Okay, so what did you tonight? We work and look at some of the slides that talk about why molecules stay together, either as a gas, as a liquid, or a solid. So different topics was discussed in chapter 12. We started with the water, and these are basically slides that I adopted from the textbook. So the textbook has a lot more slides. So I took some of them and we talk about them in the classroom. Again, called it A series used by me, Nazir. So the first one was basically discussing water and the different form that the water can have as a gas, liquid, or solid. Again, sometimes we like to show a picture of them. So we say the gas is basically few molecules. Liquid has more, of course, but they move around. And as a solid, basically they're all stuck together and they don't move. Now, properties, we talk about properties. We said the density and etc., etc. And then we talk about a little bit about dispersion. We said, what's the dispersion? And dispersion will explain why some molecules stays as liquid. For example, we talk about octane. So octane is a liquid. At one point, octane molecule could have a partially positive, partially negative part. And so they stay together because the opposite charge attract each other. So the molecules stay there as a liquid, and the more and bigger they are, they can have basically bigger shape and they can disperse and have a positive negative charge easier than if it was a small molecule. Compare that to, for example, krypton versus helium. Krypton is bigger, a lot bigger. So it has basically a higher dispersion force for krypton than helium. And we use that to explain, for example, that octane has higher boiling point than pentane. And we said if you compare that to propane, which is somewhere here, so that would be basically gas. And then we jump over the dipole-dipole interaction. We said dipole-dipole interaction is also explained why acetone stays as a liquid, because again, we have an imbalance of charges, positive and negative, and the opposite charge, or delta positive versus delta negative, they attract each other. We talk about the space filling models versus potential models and different way you can show the molecules. And we talk about, again, that this dipole-dipole attraction can change the boiling point and affect the boiling point, makes the boiling point higher. And then we jump on, so we talk about gasoline. I talk about gasoline in the tank, and I said the gasoline in tank, water in the tank is not good because they don't mix and it could potentially damage the engine. Then jump on hydrogen bond, the favorite subject of hydrogen bond, and frozen water, and it stays on top. Diet Coke and Coke at the McDonald's, remember the ice cube stays on top. And hydrogen bond causing that. And we said the hydrogen bond, basically we showed as a little dotted line, and the bond between the oxygen and hydrogen are basically solid lines that shows electrons are sharing between the oxygen and hydrogen. And that's what a loose structure is. Very simple, using lines and letters versus space modeling or potential. So these are a little bit harder to draw on daily basis. So hydrogen bonding is important. We talk about that, effects of that. On ethanol, we talk about ethanol. So hydrogen bond causing ethanol to be a higher boiling. And it's a nice thing when you go to the bar or you're getting home and have a glass of beer, it stays liquid, which is a good thing. we're not going to drink dimethyl ether because it's a gas, so I can't drink that. But ethanol we can drink. And then we talk about a little bit about the ion dipole forces. We said the chlorine and sodium in water can stay and dissolve in water because the attraction between Cl minus here, it's hard to see it, but it's Cl minus and sodium plus. They attract the opposite side of the water molecule and they get dissolved because even though the attraction between sodium plus and Cl minus is very big, but water could separate them from each other. And that's what we call it ion dipole forces that dissolve sodium chloride. Then we jump, another subject was viscosity. We said viscosity is how thick the material is and how the flow of the material, and use honey as an example. And here we have example of different viscosity, different gasoline and pentane, etc., etc. And you can see as molecule gets a little bit bigger, the viscosity goes higher. And the unit we use is poise. So poise is used for viscosity. And then we talk a little bit about factors affecting viscosity, and that basically is temperature. Temperature affects the viscosity big time. Now, there are a couple of slides that I ask you to look at it yourself. So I'll talk about them in my second part, and that starts from vaporization, how things vaporize as a molecule.